joined together simply. It's not a very new idea. In fact, it was recorded in the 11th century. And it was first used for the situation where you had a big room, like 10-meter room, 10 meters, let's say, by 10 meters. That's like the apple cube. But the timber lengths were 8 meters. So you would take a piece from here, and you would bring it to that point, okay, and then stop, and then take another one, and go from there to that point. And then the third one you would take from there to that point, and then the final one, that final one from there through to there. So you end up with a kind of a what do you call it? A windmill-like kind of an arrangement. But you can expand it outwards for as long as you like, and you can use even different materials. You know, you could use maybe steel plate, and then you could use plywood, and then you could use aluminium, and then you could use glass. Yeah. In fact, flat plate material is quite nice. You can also profile it. Well, if you want to make a really funny, like, up and down surface here, or here, or underside, you just get the flat plate and cut it on a CNC machine to the shape that you want, top and bottom. You then need to clad it, obviously, in something, so that's another type of problem. But you could get the basic framework for a surface which was not flat, very simply, very easily. And you could even make it, it's got so much, it's got no fine tolerances, it's very crude. You can just slot them into each other because it's all just simple bearing. There's no kind of bending there, it's just simple, one on the other. It's a three knife trick. If you ever get 3 glasses and 3 knives, you can actually join them, overlay them one another so that they support each other in the middle. You can try it, and then you can put the bottle of wine on the little triangle in the middle, and it'll support it. That's the principle. Use a cheap bottle of wine. So you can see there's the principle here. You get the little hanger. This one's continuous, running through. Then that one's continuous. And it suits glass because glass likes sort of low loads in the glass. So this keeps the loads low. If that was a continuous beam, it would be higher strength. You need a bigger element. This is all this same Sentry glass laminate material in between the glass, which is very strong. With those structures, you do need to support them, you know, the reciprocal structures, until you put the last piece there, right? You can't sort of put one from side to side, because none go from side to side, you know. So you need to, and then put the last one in, and then you're there. So there's a lot of work involved when it's glass. And these are sort of embedded metal pieces. You can see a bit more clearly there. So on plan. And this is the red staircase in Times Square, which, imagine them all slipping down when it's wet. It would be not much fun. If you go there, it's an interesting architectural thing to go to the top and look back down the square, because you suddenly have this refuge from, from all the people in Times Square. But at the same time, you have the experience of it. It's quite nice, actually. It's a very clever idea. A couple of Australian architects did it as a competition. It took 10 years to build it. It was a millennium competition and was not finally finished till 2009, 2008. Lots of arguing about cost and metal treads, resin treads, but finally they accepted that glass was the best answer. It's quite nice, really. Different colors, textures. This is Bloomberg red. to keep the project on track, we needed finance from the Manhattan City Council. That's the mock-up. This is using the glass by Wesley Deck, by the way. This is the expensive stuff, the slippy stuff. And that's our design team with the less expensive one. And this is showing it. It's actually sitting on glass beams which are cut to the step profile. They're laminated. But a kind of unfortunate aspect of, the Australians unfortunately didn't get to carry out the project because they weren't licensed or anything in New York, and New Yorkers are very jealous about everything they do. So it was given to a local architect there. I mean, he was enthusiastic, but it's different from being the author somehow. If you're the author, then you don't give up things at all, maybe easily. But we ended up with what originally we wanted was the light to come down in the day right through the red steps, right through the glass into the space below, and then at night we thought it should be lit from the inside so that they glowed from the inside. But because of, I don't know, some silly decision, they ended up putting an aluminium tray between the beams underneath the red steps so that any water that got through the steps was carried away. So it's like a gutter, which is all right. I mean, they lit the gutter so the glass steps looked fine, but all that area underneath and the glass beams and the whole thing has really got lost, And it could have been, I think, quite different, much stronger if they'd managed to fight for it a little harder. This is a big GRP booth itself, which was, and this is reality imitating fiction, because there was a movie about New York in 2050 or something, and they were looking for things that would be built by then. And this they used as one of their stage props. I don't mean this, I mean they built their own tickets pavilion. Our tickets pavilion cost $3.5 million. Their ticket pavilion cost $5.5 million. Their ticket pavilion lasted 6 weeks and then disappeared. It's the movie business. I mean, they didn't even build a real staircase. They built, imagery. But that's apparently how much they spent on it. But in the movie, a taxi crashes into it. And because it's glass, it was great. It demolishes it. And about 2 weeks after the film came out, a taxi came through the barrier there. And that's the internal glass wall just gone up. We just missed it by a fraction. So there's now a line of bollards kind of down both sides to stop the same in the future. You can see it's big. I mean, you can't even see the glass beams, can you? You just see the aluminium things. There's actually 6 glass beams there, all with these step profile, if you look a bit carefully. What's that? What? I think it's probably time to go home, right? Was it time to go home? Do you want to go home? Yeah? Shall I just quickly flick through the rest and stop telling stories, right? I heard interest. Someone woke up. These are impressive. They're 4 meter high, 4 laminate sheets of glass, and they hold up all the beams that are holding up the treads. They're just flat sheets of glass. This is the big wall I was telling you about. This was our first project in America. This whole building we did, but the bit I'm going to tell you about really is just that wall. That's the one with the vertical cables, right? And the grid shell roof was nice as well that we did. But that's the wall finished. But that's the process. You can see that just vertical cables. And the reason for that is if you have horizontal ones, then you'll get distributed loads into this arch which are differential, which means it will go like that. It won't be all the same, you see. Whereas with the weights, it just always keeps it at the same load, you know, which for an engineer and an arch, I have never seen an arch. They're theoretically the perfect structure, but they are never theoretically perfectly loaded. And therefore, they're always bending, right? This is the first arch I was ever able to design that got no bending in it, or very little bending, which means that size, it's all in compression then, and when something's in compression, it can be quite small. As soon as you put unequal load, it goes into bending, and then it needs to go quite deep. So we could build something which was really quite small there. That's the principle. It shows the cable being deflected by the wind and the weight rising up, and then it would come back down again. And the other thing that is interesting as an idea, I guess, is deflection, because someone says, how much should you let a piece of glass deflect? You say, I don't know. What does it say in the book, or something? Anyway, you probably say span over 200, so if it's like a 5-meter span or something, you divide 5 by 200 and get 25 millimeters, right? So you should really only make it go 25 millimeters, right? This is 30 meters high. What's 30 divided by 200? 300 millimeters, maybe. Right, is that right? Can I count? No, it's 150 millimeters, right? 150, right? So it's 150. So if you were reading, if you didn't have any idea about really what happens with glass, you would sort of look at the book and say, maybe we'll maybe let it deflect 150 millimeters. This is actually deflecting 1 meter under full wind, right? And the reason is that each piece of glass in that big grid, although it's moving 1 meter, in itself, it's only bending a little bit. In fact, not very much at all. So you can actually, as long as you know what each piece of glass is doing, and as long as it's not breaking, and as long as the movement is not causing damage to any of the finishes or anything else, then the deflection is fully acceptable. This is them building it. So that's the cables being hung. This is the arch, which is just propped off the roof for lateral. And then you hang the cable on the arch. And then you put these fittings in, which are corner patch fittings, just to hold the corner of the glass. That's it. Sort of casting stainless steel, fixed back to the cable. All the same, very simple. Laminated glass. And these are the weights. They're up to about 12 tons is the heaviest one. They have different degrees of hollowness, so they all look the same, but they're actually different weights, depending on the length of the cable and where it is in the assembly. And you can actually eat down here underneath them. And so when the wind blows, you can see them going up and down, Bit scary. So you can see it's very simple, really. And was a big kind of design leap. It hadn't been done before. But there's now lots of them. And that's the other thing. Once you do the first one, then everyone piles in. They realize everyone's going to want one. And this, you actually take, because it's parallel cables rather than the tennis racket type cable, you can actually go around corners with it. You can curve it like that. More cable structures, more work in Japan. That's their mock-up, the wonderful The other thing they do in Japan, which is interesting, and it's to do with, the Japanese are very protective of their culture, very insular in a way. They're very welcoming, but, there's Japanese and there's everybody else somehow. Well, they kind of lived alone for 200 years, didn't they, in isolation. So they built this kind of wall. And it kind of means that they're kind of impenetrable at some level, but they're very wonderfully united when it comes to the disparate building industry that we have. All right? You'd never get it happening in this country, but what happens is that the big main contractors, they get together once a year and they choose which architects and which buildings they're going to fund. And they will spend up to 5 times the budget on those buildings. They will give the architect 5 times the budget to experiment in which way he wants to experiment or she wants to experiment. That's how they progress their technology. They give it to the design team, not how do you make mortar in a better way or something, but how do you actually, Toyo Ito's media center, for example, was the one example. It was researched by a woman called Diana Buntrock. She did a comparison between the American industry and the Japanese industry, and she discovered this whole thing. It's a fantastic way, and you could only really do that if you know that you're all working together, that you're a group, that you're not, So they would spend money like this. I mean, there's a ridiculous amount of money to be spent to build this mock-up, but this is what they would do, and you think, where do they get the money? And that's the secret, they really do, they divert money, and they help each other, they support each other. They won't let each other go down in the same way that we will. Metal work, as I mentioned earlier, it's usually always visible, and therefore usually always has to be specifically designed for the task. As you go to Kew Gardens, this is another example of the curved parallel cable wall where we're supporting it's also stacked glass. That sits on top of that one. Otherwise, that bracket would be very big. Parallel cable going around the corner. We've even got a horizontal cable wall. This one, again, the glass is stacked. That sits on that, they all sit in each other. And the only thing that restrains the wall are these horizontal cables. Right? And we've even got a little lever here so that the weight can be reduced due to the lever principle. But it means it moves a lot so that when, what the client wanted was so you'd actually see them moving up and down. So they put the sort of city medallions on them, and when the wind, because it's magnified, you really do see them move. They move around. V&A, if you go down there, the Daylit Gallery there was based on this principle of making the beams translucent and the glass in between clear, which gives quite a nice rhythm. But one of the things with the V&A is that the roof is curved, and it means that if you start a beam and stop a beam at the same level, it's not only curved, it is curved in such a way that the beams keep changing length. Right? So each time you go around the corner, you get a 9-meter beam, and the one next to it's 7 meters or something. Different lengths. So different lengths have different angles. Right? If you're going from the same level here to the same level here, and you've got a longer beam, you end up with a different angle. So 2 adjacent beams are at different angles. And when we first looked at it, we thought, oh, that means the glass is going to have to twist a little bit. And we thought, it's not much, it'll be all right. So we went quite a long way down the design and pricing and bidding and everything. And then we had the realization that actually it was 150 millimeter movement of one corner down while you held the other three. That's quite a lot, isn't it? Not 150 millimeters, 3 meters long sheet. So we thought, they can't do that. You're going to have to bend it in an oven. Make all these panels. They're all different. Each one will have a different mold. It'll cost a fortune. So the job was going to be radically changed at that point until we had playing around with a piece of card and realized that actually, if you push this down, the edge remained almost straight. It's a funny phenomenon, but our problem was not the glass being stressed, by the way. We'd already worked out the glass stress could cope with this deflection. The worry was that the edge would become so curved that the insulated glass unit would actually fail, because it got too curved. And so anyway, we convinced ourselves that this would remain almost straight when you pushed it down. And we finally got the client to make a sample, this is at 3 meters long, about 800, 900 wide. And we put it in a machine to bend it. And so that's the panel, and this is the corner that we need to go down. And it took, funnily enough, almost exactly the weight of one engineer on the end to bring it down 150 millimeters. And it did actually go down 150 millimeters, and that is it. You can see the edge is nearly straight. Yeah, it's actually laminated and insulated. The bottom sheet is laminated because it's overhead, so if it broke, it must stay there. The top is toughened glass, actually, and this is insulated, so there's an air gap in the middle. And with all insulated panels, they do not like you to deflect the panel over a certain amount because it stresses the edge seal and it can break down. So that was our big worry, that they wouldn't warranty it. But in this machine, that is a straight edge all along there. It's virtually, it's quite, we were amazed when we discovered it with the model, but it did actually do it. It's called cold bending. It means that you can order the glass just the shape you want, and then when you get on site, you've got to hold it there and sort of, anyway. They can do it, they can fix it, and they were amazingly good at fixing it as well. Seattle Library, yeah, that's a story, but I'm not going to go into it really. It was another of those stories of bringing the cost down from 24 million to 12 million by making one simple move, design move. And it allowed them to have shading in the building. Could you believe they designed that building with no shading? It's like miles of glass. This is the Shepherd's Bush, what's it called? Westfield Shopping Centre. That's it, but it's in China. And what's amazing is these guys, when we went there, the cladding contractor won the project, and he said, we said, well, who's going to build the roof? And he said, I've got a steel fabricator who can build the roof. We said, can we meet him? So he comes along, and we said, have you built one of these before, They're quite complicated. No, he said, I haven't built one before. So we said, okay, how are you going to do it then? How are you going to make this connection here? It's all about the connection. He said, I have a very big pipe. So he said, I think he's quite got the idea here. So we're kind of giving up, and we're suggesting to the client, if he wanted this roof, he'd better come to Europe and get Sealy to do it or something. And anyway, they found this Chinese guy, Dr. Zhu, Professor Zhu, and he came in, and we thought, there's no way that anyone in China is going to be able to sort this out, is there really? So he gave us this slideshow, and he had these fantastic pictures of the Shanghai Expo entrance structure, which has got these great big funnel-shaped, beautiful grid shells, 90 meters in diameter across the top, like 50 meters high or something, big, enormous things. And he took us through, and then he had a wee video at the end, and he was being interviewed by the BBC. They were saying, this is great, wonderful. How did you do all this? And he started to cry. He was such a fantastic guy. I mean, he was so moved that he'd actually achieved it. And he knew what it meant, And this, he was told to start, he had to do his own design over and above the design that had been done, because he'd got to sort it all out. And he was given from the 15th of October, he had to be finished by the 15th of December, the same year. Okay? And he said, no, I can't do it. It's, 15th of January. And I went to his factory in China, and it looked like no one had been in there for about 20 years. It was like thick and dust and stuff. And he'd been talking about all these CNC machines that he'd invented himself and had used. I seen it. And there they were. They were like it's kind of Heath Robinson objects, really ancient-looking objects. They didn't look like anyone had been touched them forever. And he's telling me they're CNC machines, and I thought, no. And then he took me to show me the expo, and I thought, wait a minute. How does that work? Anyway, he got the job, and I went back about 2 weeks later, and they make all these like individual nodes, and they're all absolutely perfectly done geometrically. And I went into his factory, and I couldn't get in the door hardly. There was people hanging from the rafters, cutting little bits of metal, and all these CNC machines had jumped into life, and they were all brilliant. You got the whole thing sorted. And these nodes were rolling out. He'd had wagons loaded of them already to go up to the site. So I was really astonished at how it's a bit rough. I mean, if you look at what Sealy's done and you look at what they've done, it's a bit rough, but I mean, it's quite extraordinary where they've got it to, or what they're willing to attempt. I mean, the geometry is not easy, it's sort of getting all that sorted out. And the funny thing is, like here in this part, there was absolutely no coordination. I mean, that's the biggest issue in China is that, the concrete guys do their stuff and the steel guys do their stuff, and the architect doesn't care. And nobody has actually looked at where the two bits come together. And so, down here, we'd already sorted out that, the steel went below the concrete. And we said, well, where does the water go? Inside building. No, not inside building. So, you get areas like this. We said, this is, even that we thought we'd sorted out, but no, you still had an area that was low. So we said, this won't do. He said, no problem. He comes in, gets his guys, cuts it all out, lifts it up, turns it around, and rebuilds it. Just not a problem. Quite extraordinary, really. This is Shenyang. Anyway, these are load-bearing glass walls where the glass is a bit like the Tickets Pavilion. So it's a bit more dramatic because this looks like a solid roof, And these are the flat glass panels just supporting the steelwork. So you can avoid the column in the corner, really, and get the nice view. And this is where it was used for a real technical reason, which is a airport observation tower. And the glass holds up the roof, and there are no mullions, you see, so they can get a better view, 360-degree view. around there. It's quite high as well, it's about 4 meters. And it's actually insulated as well, panel. There's a trick, actually, because you fix the glass at the bottom and fix it at the top. So structurally, you do something which makes it much stiffer, because they didn't want this to deflect much either, because that disturbs the vision. And that's just some fancy glass, and then we can say thank you. Good, thank you.